I'm going to talk about writing ionic equations. So first off, what is an ionic equation? Well, an ionic equation is just an alternative way to write a chemical equation. And a chemical equation is just a representation of a chemical reaction. You're probably used to seeing chemical equations written in the molecular form. So a molecular equation shows all of the substances in their neutral form. So as actual neutral compounds, whether or not that's actually how they exist for the process. When we have reactions in solution that involve ionic compounds or acids, those substances don't actually exist as neutral compounds. They break apart and exist as ions, or at least partially, depending on if it's a soluble or insoluble substance or a strong or weak acid. And so to better represent reactions that involve ionic compounds or acids in solution, we can write a chemical equation as a complete ionic equation. And the complete ionic equation shows all of the substances as the majority exists. So if you have something that is a strong electrolyte, such as a soluble salt or a strong acid, those things break up into ions completely, or at least nearly completely. And so when we write those things in a chemical equation, at least in the complete ionic form, we'll break those up into ions instead of showing them as neutral substances, since that's how the majority exists. Whereas weak electrolytes or non-electrolytes, those things either exist as neutral compounds or the majority does, so we'll leave those as neutral substances in our complete ionic equation. Now, that can get a little bit lengthy when you have several strong electrolytes in your reaction. So there's a simplified form of a complete ionic equation, and that would be the net ionic equation. The net ionic equation only includes the species that are actually participating in the reaction. And so the things that are changing from the reactant side to the product side. So sometimes you'll see when you write the complete ionic equation that there's some substances that are exactly the same on the reactant side and the product side. And those things would be called spectators, or sometimes we'll call them spectator ions. And so since nothing's happening to them, we're not really interested in that. We want to see what's actually changing. And so you can convert your complete ionic equation to a net ionic equation by canceling out all the spectators. And then what's left are only the things that are changing. For our first example, we're going to look at the precipitation reaction between sodium chloride and silver nitrate. So we're given the molecular equation for this precipitation reaction, and we want to convert it to a complete ionic equation and then convert that to a net ionic equation. So to do this, first we need to identify the strong electrolytes. And with this reaction, you should be able to see that all of these substances are ionic compounds. And so it should be pretty easy to figure out the strong electrolytes, because for ionic compounds, a soluble ionic compound is a strong electrolyte. And since we're given the phases in this reaction, the phases directly tell us. So all of these ionic compounds that say aqueous, these first three compounds, those are soluble salts. And soluble salts are always strong electrolytes. Whereas this one that's written as a solid, the silver chloride, that is an insoluble salt, and insoluble salts are always weak electrolytes. So to convert this reaction to a complete ionic equation, we need to break up the strong electrolytes into their ions, and we leave the weak electrolyte as is. So to do that, we would break up the NaCl into Na plus and Cl minus. We would break up the silver nitrate into silver ion and nitrate ion, so Ag plus and NO3 minus. We would break up the sodium nitrate into Na plus and NO3 minus, and then we would leave the precipitate, the AgCl, as is. And that would be our complete ionic equation. Now, from that complete ionic equation, we can get the net ionic equation by canceling out the spectator ions. And so you have to look for the things that are exactly the same on both sides. And so in this case, what you should see is that you have a sodium ion on both sides of the reaction that have not changed, and you have a nitrate ion on both sides of the reaction that have not changed. And so those are all our spectator ions. So we can cancel those out or eliminate them from the reaction, and that will leave us with our net ionic equation, which would be Cl minus plus Ag plus or going to AgCl solid. And so that would be our net ionic equation. Now, with all of these substances that I've written, you should notice that the ions are always written as aqueous, and so when they break apart in ions, those ions are dissolved, and so their phase is aqueous, whereas the solid that remains intact is still a solid. And everything that breaks up, it's really important that you put the charges, because when those ions break free of one another, they do have a charge, whereas when they stay together, we don't put the charges, like in the AgCl. Next, let's look at the reaction between barium chloride and sodium sulfate. So this is another precipitation reaction. This time we're forming the precipitate barium sulfate. And if we want to convert this equation into a complete ionic equation, we need to identify the strong electrolytes and break those into ions. And so out of all of these compounds, these are all ionic compounds. And for an ionic compound, if it's a soluble ionic compound, then it is a strong electrolyte. And that would include all of these substances that are written as aqueous substances. So all of these are soluble salts, meaning they're strong electrolytes. So those are the things that will break up into ions to get our complete ionic equation. So our complete ionic equation, first we're going to break up barium chloride into Ba2 plus and 2 Cl minuses. So you do have to realize that subscript 2 is there because we need 2 Cl minuses in barium chloride, not that it's a diatomic ion. And then next, we break up sodium sulfate into 2 Na pluses and 1 SO4 minus. Again, that subscript of 2 with the Na is telling us we need 2 of those Na pluses to balance out the 2 minus of the SO4. So not that it's a diatomic ion. And then the barium sulfate, since that's a weak electrolyte, it's an insoluble salt, that stays as is. And then lastly, we have our sodium chloride, which is a strong electrolyte, a soluble salt. So we break that up into Na plus and Cl minus. And since we have 2 of those NaCls, it's actually 2 Na pluses and 2 Cl minuses. Now, we can identify our spectator ions. And so we look for the things that stay the same on both sides. And in this case, we have chloride ion on both sides, and we have sodium ion on both sides. We actually have 2 of each on both sides. And so all of those cancel out. And then that will give us our net ionic equation. And our net ionic equation would be Ba2 plus SO4 minus going to barium sulfate. Okay, now we're going to do one more precipitation reaction between cobalt 2 chloride and sodium carbonate. And so that forms a precipitate of cobalt 2 carbonate. And so we want to convert this molecular equation into a complete ionic, then a net ionic. And all of the substances involved here are ionic substances. So again, any of them that are soluble are strong electrolytes. And so that would be all of these that are indicated as aqueous. These are all soluble salts, meaning they're strong electrolytes. And so the complete ionic equation would be CO2 plus 2Cl minus, because again, this breaks apart into the cobalt 2 ion and 2 Cl minuses, so not a diatomic chloride. It's two individual chlorides. And then plus 2 Na plus CO3 2 minus. And again, you get 2 sodium ions for every 1 carbonate ion, not a diatomic sodium ion. And then that is going to form the solid cobalt 2 carbonate. And then we break apart our sodium chlorides. And since we have 2 sodium chlorides, we get 2 Na plus and 2 Cl minus. And so that would be our complete ionic equation. And then if we identify our spectators, we can then eliminate them and get our net ionic equation. So if you look on both sides, you've got 2 chloride ions on each side, and you have 2 sodium ions on both sides. And so those we can cancel out or eliminate those, and that will give us our net ionic equation, which would be CO2 plus CO3 2 minus going to COCO3 solid, so cobalt 2 carbonate. Okay, we'll look at one last reaction that involves all ionic compounds. So in this case, we have copper 2 sulfate reacting with sodium chloride. And the products that are given to us are copper 2 chloride and sodium sulfate. But you should notice this is a little bit different than the last ones in that all of these have phases of aqueous. What that indicates to us is that these are all soluble salts, meaning they're all strong electrolytes. Now, after you do several of these, you'll realize that if everything is a strong electrolyte, that means everything breaks up into ions, meaning in reality, there's no reaction. And so really, there's no point in writing this out. But sometimes, before you really fully understand this, it can be helpful to take this reaction that we've written that looks like something's happening and convert it to a complete ionic equation. And when we convert it to that complete ionic equation, it should become a little more obvious that nothing's really happening. So let's do that. For our complete ionic equation, we're going to break everything into ions. So the copper 2 sulfate is going to split into Cu2 plus and SO4 2 minus. The NaCl is going to break up into 2 Na pluses and 2 Cl minuses. And then the copper 2 chloride is going to break up into Cu2 plus and 2 Cl minuses. And the sodium sulfate is going to break up into 2 Na pluses and an SO4 2 minus. So now, usually what we would do is we would take this complete ionic equation and we would convert it to a net ionic equation by canceling out all of the spectator ions or eliminating those spectator ions. And so if you look for spectator ions, what you should see is there is a copper 2 plus ion on both sides. There's a sulfate on both sides. There's 2 Na pluses on both sides. and there are 2 Cl minuses on both sides, meaning that everything in that reaction is a spectator. So everything cancels out, so that's why there's no reaction. Now we're going to switch over and do an acid-base reaction. And so this acid-base reaction involves hydrobromic acid and calcium hydroxide, and those react to produce water and calcium bromide. So for this, identifying strong electrolytes is a little bit trickier. You can't just assume that a phase of aqueous means it's a strong electrolyte. So acids are always written as aqueous, and sometimes bases are written as aqueous even when they're weak electrolytes. So you do have to be a little bit careful. In our cases, the acids are what you need to be cautious of. So hydrobromic acid, you need to know, is this a strong or a weak acid? And it's a strong acid. So that means it is a strong electrolyte. And then calcium hydroxide, well, you can think about that as a base, but it's also an ionic compound. And so since it's an ionic compound, we can look at the phase, and it's a soluble ionic compound, meaning it is also a strong electrolyte. Then we have our H2O, and H2O is a molecular compound, and since it's a molecular compound, that means it is a non-electrolyte. And then lastly, we have our calcium bromide. That is an ionic compound, and since it's written as aqueous, we know that's a soluble ionic compound, meaning it is a strong electrolyte. So to convert this molecular equation into a complete ionic equation, we're going to take all of the strong electrolytes and break those apart. So that would be our HBr, our CaOH2, our calcium hydroxide, and our calcium bromide. All of those things are strong electrolytes, so we're going to break those up. The H2O, since it is a non-electrolyte, we will leave that together. So our complete ionic equation is going to be 2 H pluses plus 2 Br minuses, because if you look at your equation, you've got 2 HBr's, and for each individual one, we get an H plus and a Br minus. So when 2 of those break apart, we get 2 H pluses and 2 Br minuses. And then our calcium hydroxide breaks up into Ca2 plus and 2 OH minuses. And then we get our H2O, which we leave together. And then we have our calcium bromide, which we break up into Ca2 plus and 2 Br minuses. And then we want to convert this complete ionic equation to a net ionic equation, so we need to identify spectator ions. In this case, you should see that you have Br minus on both sides, actually 2 Br minuses on each side. And then you have Ca2 plus on both sides. And so those are the things that are the same. Those are the things we're going to eliminate, the spectator ions. And so then that will give us our net ionic equation, which would be our 2 H pluses plus our 2 OH minuses going to our 2 H2O's. And that would be our net ionic equation. Now you could simplify that and get rid of the coefficients of 2 all across that equation. You could reduce it down. Either way is really correct. Some people will say you have to reduce it. Some say you have to leave the 2's there. I think either way is fine. The 2's come from the original equation, but reducing it down is the more proper way to report things, or to report chemical equations. The final reaction we'll look at is the reaction between hydrochloric acid and sodium hydrogen carbonate, or sodium bicarbonate. So this reaction is between an acid and a carbonate salt. And so what you should see is this is a gas formation reaction. It forms CO2 gas. So this reaction, we're going to convert the molecular equation to the complete ionic equation and then the net ionic, just like we've done with the others. So first we need to identify what kind of substances, what kind of electrolytes we have. So first we have HCl, which is a strong acid, meaning it is a strong electrolyte. Then we have sodium hydrogen carbonate, which is a soluble salt, meaning it is a strong electrolyte. And then we have H2O liquid, that is a molecular compound, so it is a non-electrolyte. And then we have CO2 gas, that is also a molecular compound, thus a non-electrolyte. And then sodium chloride, which is a soluble salt, meaning it is a strong electrolyte. So to convert to the complete ionic equation, we need to take our strong electrolytes and we're going to break those up. And the remaining non-electrolytes we will just leave as is. So for the complete ionic equation, that gives us H plus Cl minus plus Na plus HCO3 minus, and then that's going to H2O plus CO2 plus Na plus Cl minus. So I've broken apart all of the strong electrolytes into their cations and anions, and then I left together the non-electrolytes, the H2O and the CO2. And then, if we want to convert this to a net ionic equation, the net ionic equation will be what's left when I eliminate the spectators. So in this case, on both sides, we have Na plus, and then on both sides, we have Cl minus. And so I would cancel those, and what I would be left with is H plus HCO3 minus going to H2O and CO2. And that would be my net ionic equation.